So, welcome back to one more lecture on introduction to soft matter. Last time we were discussing the issues concerning constitutive modeling, and we are in particular discussing the principle of objectivity. So, one of the last things that we were reading out was this line by Professor Suo, where he says that we construct variables invariant with respect to rigid body motion. Later we will use these variables to construct rheological models invariant with respect to rigid body motion. And here we had just stated that equivalent observers are two observers who are basically related by a general rigid body motion. So, rigid body motion, you can show that, and I am not going to show it here, but it can be shown that rigid body motion basically involves a rotation and a translation. And a translation. So, let us say you have two frames, F is your current frame, and we will denote all quantities in another frame by F star, and that these two frames are equivalent observers and they are related to each other by a rigid body motion. Now, rotation between two frames, rotation between two frames can be represented by a matrix. So, 3-dimensional, if you have 3-dimensional space, then the rotation matrix will also be 3 cross 3. So, the rotation between two frames can be represented by a matrix, let us call it Q, and I just put a double bar here to indicate that this is a matrix T, where Q into Q transpose gives us the identity matrix. Okay. So, Q is also often called an orthogonal matrix. So, now if you have in the rotated frame, you can represent, let us say, the new location for a particle, or let us say you have, so let us say you have a particle located at x, and you have another frame which is rotated and translated with respect to the previous one. Then what is the new position for that same point in the rotated frame, the rotated and translated frame. So, we can actually write this relationship that x star, which is the position of the same point in the rotated frame, can be given as some translation, we will just call it by c, and t just shows that it can be a function of time, plus the position of this point with respect to some origin multiplied by q, where q is the rotation matrix. Okay. And here no loss of generality is incurred, and I will just make a note here. So, no loss of is incurred by assuming that O is fixed. Okay. So, let us say that you have a measured field phi in the reference frame F, and that field now becomes phi star in the new field, in the new frame, right. So, let a measured field phi be phi star in the frame F star. And let this be a scalar quantity for the time being. If it is a scalar quantity, then we say that the scalar fields are invariant if they retain the same value when you change the frame. So, we will say that scalar fields such as density, for example, are invariant to a change of frame. Which implies that in the rotated frame or the translated frame, if you measure in the F star frame, you are measuring a density which is phi star, that should be the same as the density that you are measuring in another frame, in an equivalent frame. So, from this we can make our first rule for scalars, and that rule says that hence for invariant scalars phi star equal to phi. So, this is an important point, right, because even though this is a very simple idea, you must understand, or we must have a situation or a constitutive relationship where the change of frame cannot affect simple quantities like viscosity. So, whether you are measuring the viscosity of water on planet Earth or Mars or somewhere else, that it is a material property. Okay. It cannot change with just because you have changed to a different spatial location and maybe at a different point of time. You cannot change that. Again, as I said, this is an axiom. So, this is something that we believe is true, and we believe, and we build our equations and our theory based on this. So, for invariant scalars, this simple relationship holds. Okay. But this relationship will always obviously not remain as simple for other quantities. So, let us now discuss the case of vectors. So, let us take our old idea of vector, which is that you have 2 points and this is the displacement vector between the 2 points. Okay. The point here is given by some x. These are the coordinates in one frame, reference frame. When you change to a different reference frame, the coordinates also change. So, you have now this coordinates in the new frame. Similarly, this is another point, let us say this is y, and in the rotated frame, in the new other frame, you have rigid body translated and rotated frame, you have y star as the new value. Now, displacement we have to understand is something that is truly frame invariant, right, because otherwise how will you even discuss lengths? If displacements are not the same in all, for all observers, how can you even agree upon a length, right? So, displacement is so the position vector of a point may not be independent of the frame, because that is tied down to where you are measuring it from, but the displacement vector between 2 points, that is truly frame invariant. So, what we call separation is frame invariant. Okay. So, we had just written above the equation for the change of reference frame. So, let us write down what x star is in terms of x. Okay. So, we had said that x star is equal to sum C t plus q x bar minus O bar. Similarly, I can write it down for y, right. the same equation. I am going to replace x for y now. So, what is the so we know that y, this displacement vector is going to be invariant. So, if I subtract the two, I end up getting right. Okay. So, this is important here now. So, this we know, since we know that the displacement vector is invariant, we know that if we have to calculate the invariant, if this form is the form of invariance. Right. So, we now what we are going to do is we are going to say, looking at this, is that a vector is invariant when it transforms as so let us say you have a vector u, when it transforms as this rule. Okay. Now, there is one thing that I just like to point out, and that is sometimes an issue between different books and different presentations by different authors, that here what we are trying to do is this u, y star etcetera, this relates to the position, the coordinate values, right. So, if you have, you can think of it as maybe a column vector with 3 points for the x, y and z coordinates. So, these are actually the values itself, and it does not, it is not the abstract quantity vector itself. So, I am taking I am adopting a scheme that is, or I am adopting a formulation that is taken by Phan Thien and some of the other authors. Some other authors like Suo, they say that it is better to write in terms of the components. So, I just wanted to point that out. Okay. So, good. Displacement is invariant, right, but what about velocity? Is it also invariant? So, let us look at, let us ask ourselves a simple question. Okay, the question is, by the way, this q is question. Okay, so, I will just maybe write down question, because we have already another q. Okay. So, the question is, how does velocity transform? So, we know that we have previously written that expression. We let us just rewrite this. And this is also a function of time. Okay. We have to discuss the velocity. So, velocity, your transformed velocity, is nothing but the derivative of this, the d dt of x star. And if you take the derivative, and here this is, remember that this q can also be a function of time, and you have x also a function of time. So, you have to apply chain rule. So, first time maybe we will just take the derivative of q. So, we have q dot and then the second time we take the derivative of x. So, we have x dot and O is fixed, as we had just said previously. There is no loss of generality in assuming that that is just fixed, then you have c dot t. So, this implies, if we just clean out this expression bit, this quantity is the velocity, right, in the other frame. So, you have transpose, this is the velocity plus. So, I am just rearranging the terms here, and you will probably can understand why I am doing that. Right. And we had just said that a vector is invariant if it transforms as this equation previously, right. So, this was our important equation. But we see that when we apply it to velocity, you now have this here an extra set of contribution here. So, velocity is not frame invariant. That is something you should expect also, right. If you think about it, velocity is a very important frame dependent frame sensitive quantity, right. Okay. So, what about acceleration? So, we will just maybe do one more question. What about acceleration? So, we know that we have already written that expression V star is equal to Q bar T V bar plus Q dot T. So, A star, which is now going to be the derivative of this, we are going to have to take the derivative again. So, let us see what we get. We will get Q dot T into V plus Q dot. So, this time we differentiate the other term, we get acceleration, okay, differentiating the first one, and then the second case, second term I am differentiating the first one, applying chain rule, plus sorry, by the way I missed this. Right. So, we can see that contrary to our expectation, had this been invariant, then only this particular term would have been there, but we have so many other terms. So, acceleration is also not frame indifferent. Okay. So, we will make a note. So, acceleration is also not frame actually frame sensitive. So, we see that despite the fact that displacement is frame invariant, its time derivative is not. Okay. So, that also should make us question as to are there other type of time derivatives which might be. Okay. We will look at that later. Okay. So, we discussed scalars and we discussed vectors, how vectors should transform. So, the obvious question is how should tensors transform. Okay. So, we ask now how should a frame indifferent or frame invariant tensor transform. By the way, you might have noticed that I have used the word frame indifferent here, and somewhere I am using the word frame invariant. Now, most authors, from what I have seen, they tend to use the two interchangeably at different times. Okay. Although sometimes the principle of frame invariance or indifference is stated as a different principle. So, how should a frame invariant tensor transform? Okay. So, what is a tensor, by the way? We know what vectors are, but what are tensors? A tensor is something that can transform one vector into another vector. So, let us say you have a vector x y, then the tensor T is a transformation of this vector into another vector. And we want to understand how frame invariant tensors should transform. Okay, what should be the rule that should be governing that? So, let us say in the other frame, this is x star, this is y star, and you have another tensor now, a different tensor, and this will transform it into. Okay. So, that transform tensor should do the same job. It should take these displacement vectors and transform it to some other vector. So, we wrote down before, let us write down the relationships that we had written before also. Let us say y star now is is equal to q times of y, and if you want to put, okay, just and then x star in this case is again so we are already just writing down the expressions that we had agreed upon earlier. So, when we take this, then we know that we have this is the same as the expression that we had previously written. We are just going through that exercise one more time. So, similarly, your B star minus A star will be q times of B minus A, and this represents now the transformed. So, this is the T tensor should act on this quantity and convert it to B star minus A star. So, T star into y star minus x star should give me this quantity now, but this is T acting on y minus x. Okay. So, and now I am going to skip a step here, okay, and I want you to sort of complete this. Q was an orthogonal matrix. So, in fact, I can use that property and then I can assert that Q transpose T star into Q will lead me to T. There is one step I have skipped, and I have deliberately skipped so that you can fill in the gap here. And this implies that your T star is equal to Q T into Q transpose. And we are going to use this as a rule to say, So, this we are going to do that a tensor. So, we are going to say, so we are going to use this to make our rule. A tensor T is invariant when it transforms under a change of frame according to this relationship. Okay. So, what we have been able to do is today we came up with 3 different relationships, one for scalars, one for vectors and one for tensors. And we said that if they need to be frame invariant, then there is a certain transformation law that should govern them, and we found out what that is. We also discovered that the velocity, that while displacement or separation is frame invariant, velocity is not, and neither is acceleration. They are frame sensitive terms. So, now that we have established the rule for tensors, we will look at some quantities, some tensors, and we will try to establish whether they are frame invariant. Okay. So, we will do that in the next class. Okay. So, we will stop here today. Okay. Thank you.